Hello guys, my name is Adam Leonardo Cap and today I'm going to review a paper based on Kessence. In my previous video, I have also talked about Kessence and you can see the video just by clicking on the I button. Today the paper is very different. This paper has the very nice result which is written by Robert J. Scherrer on 2004. He assumed that the Kessence has the Lagrangian of the field and its kinetic part. The x is containing the derivative of the field and with having this squared. Because of this structure, the Kessence Lagrangian is non-canonical. Now, people have studied this Lagrangian and they have shown that this Lagrangian is perfectly describing the dark energy and solve the cosmic coincidence part. Now, this Lagrangian is only describing dark energy and there is no link with dark matter. So in order to understand the dark matter, you have to introduce some other kind of fluid, and in cosmology, we used to study this dark matter by using some kind of pressureless fluid whose pressure is not there, which is treating as a dust. So the energy momentum tensor for that kind of fluid, you can think of u mu u nu plus p u mu u nu plus g mu nu, where u mu is the velocity. Okay, u mu is defined as dx mu over dt, and this dt is cosmic time. Okay, and we are assuming that the fluid is flowing in the world line, and this world line is given by u mu, and so fluid has the same kind of speed. Now the idea of Scherrer is that if you take simply one Lagrangian with having kinetic term. Now, since in the Lagrangian we have two things, one is called field and another is the kinetic part, they are independent, they are treating as an independent variables. So he proposed that instead of taking phi and x both at the same time, what you can do, you can drop the phi and you can say that the Lagrangian with this x is enough to produce the acceleration, and as well as it will produce the dark matter part. So we will now examine that how will you understand that Kessence can unify dark matter and dark energy. Let us begin. Now first there is an abstract here. We examine Kessence model in which Lagrangian P is a function only of the derivative of scalar field phi and does not depend explicitly on phi, which is I am talking about here. The evaluation of phi for an arbitrary functional form of for P can be given in terms of an exact analytical solution. Yes, you can find the pressure of this Lagrangian and as well as you can find the rho. For quite general condition on functional form of P, such models can evolve to a state characterized by density rho, scaling with scale factor A. So you can find the energy density, and this energy density you can write in terms of the scale factor A. Okay, so this scale factor is telling you that how big the universe and how the universe will grow. But with a sound speed, cs square is very much less than 1, because if the universe was in matter dominated era, the sound speed was not much higher at all times. Such models can serve as a unified model for dark matter and dark energy while avoiding the problems for generalized Chaplygin gas models, which are due to non-negligible sound speed in these models. So what you can see that people used to define such kind of a Chaplygin gas. This Chaplygin gas has the characteristic that it can behave as a dark matter and dark energy. So if you have this kind of Lagrangian, you can avoid the Chaplygin gas and you will say that yeah, we are safe and sound. So we don't need to have. So now sound speed is very interesting property of the scalar field. The sound speed is telling you that how the pressure of the scalar field is changing with respect to its density, and because of this perturbation the field will propagate, field will have some kind of a velocity. And if sound speed is very greater, like sound speed is so much up to 1, then structure formation is not possible. You know, in universe when you look at it, there is so much structures like galaxies, nebulae and so on, very much things. So when this is possible, when the field has not too much speed, and if the field has the super sound speed, then you cannot form any kind of galaxian structure. So no matter whatever the field you have, what you can do is that in the late time your cs square must be less than 1. That is the thing they have told. So cs square must be less than 1 in the dark matter era and as well as dark energy era. So can you get these kind of things from there? Yes, we will try. So I hope you understand so many things. So I'm not going to tackle about the introduction part. What I'm going to show you that if you have this kind of Lagrangian, this Lagrangian has directly come pressure. Okay, so you can see that how we can derive this pressure, and we are modeling the Lagrangian pressure to be V phi and Fx. This is when you have Lagrangian, which is function of phi and x, and x they have given you this half del mu phi del mu phi. Now they have considered del mu phi, and in their regards, their signature is plus minus minus. So if you are writing metric term, this metric term is corresponds to dt square minus at dx squared. So when you have this kind of a structure, you will can see that this del mu phi, if you will incorporate with this thing like g mu mu, then it will become del mu phi, and this 0 component will give you just only 1, and this will become phi dot square. We will always assume that this x is must be greater than 0, the kinetic part must be greater than 0. Therefore, from here, if they have not considered negative sign, we can say that the metric has plus minus minus signature. Now, what is the energy density of the Kessence field? If you have V phi, then this is 2x f comma x. This f comma x telling you that this is derivative with respect to x. And since f is only a function of x, okay, so we are modeling that V phi is consist of some potential of the field, and fx has the kinetic terms. So you can choose fx in terms of power law like x plus x square plus x cube and so on. So we will now examine that what could be the function of fx. Now you can define the state parameter, equation of a state parameter, which I have already discussed in the many videos. Omega is p over rho, and this equation of parameter will tell you that for dark energy the EOS come out to be -1. So omega is equal to f 2x f comma x minus f. Now if your first derivative fx goes to 0, therefore you will find that omega becomes -1 always. So in order to gain omega to be -1, this fx has to be always be negative, and this is all. And you can say that okay, x could be negative. If x is 0, therefore there is no any function of f. Therefore there is only one possibility to gain -1 is your fx becomes 0. Okay, so from here you will get. Now you can also say that okay, is there any possibilities that we will cross omega so much -1, means that can we get -2, -3 or -1.03, something like that. To have this, what you can simply say that okay, if f is far greater than 2x f comma x, if it is far greater than 2f comma x, therefore omega becomes f over minus f, and again there is no way, I think there is no way I think you will get you will cross -1. That is the problem with this kind of structure, that if you want to cross, you want to make f bigger, and if you will make bigger f, then you will again converge to negative of -1. And that is the problem with this kind of theory, that the equation of a state cannot be lower than -1. And what we are found recently that this omega is crossing -1. So we will talk about it later on in the video. Now the very interesting situation here is about cs square, the sound speed. What does it tell you? It tells you that how the pressure of the Kessence is changing with respect to x, and how the energy density is changing. It is mainly saying that dp over dx, and assuming that the universe is in adiabatic, means that there is no any heat exchange between field or fluid, or no exchange between whatsoever. The field is propagating, and so it will propagate. So cs square comes out to be fx over fx plus 2x f comma s, and demand is that the cs square has to be very lower than and lesser than 1, so that the structure formation is possible. Now fx is defined as g2f over dx square. Now come to a very interesting part. I hope you have. So if we are varying the Lagrangian, suppose I'm considering the Lagrangian is like d4x square root of minus g, and let us say p of phi comma x, and yeah, this is all. So if you will derive this Lagrangian with respect to phi, what you will gonna get. And again, there is you have my kappa square r over, sorry, r over 2 kappa square and is minus c. Okay, this is called Einstein's field. Now, if you have this Einstein's field, and this will give you the g mu nu part, and if you are varying the action with respect to phi, then there is no any contribution from the Einstein part. All the contribution will carry the phi part. Okay. Now, because x has the structure like half g mu nu d mu phi and d nu phi, from here you will get this h part, which is telling you the Hubble parameter, and Hubble is defined as a dot over a. A dot is meaning that dA over dt. So with this basic, I think what does this equation tells you? The equation of motion of the field is giving you that fx 2x fx phi double dot, some Hubble parameter, and then the coefficient of v phi. Now, if you will analyze this equation 6 with quintessence and corresponds to inflation, they are telling that the kinetic part of the field is not greater, and what are saying that this and this is enough to produce the inflation, or the and from there they are analyzing the what could be the potential to derive the inflation. So the potential must be not too much steep. The field must be rolling very slowly through this potential. Now here we are not going to assume anything, and we are saying that the dynamics of the field in such a way that it will produce the acceleration. So there is again nice paper of this kinetic Kessence, in which they have shown you that the Kessence field can derive the inflation in our universe. So we will talk about it later. Now, this is the first Friedman equation, in which it says that the Hubble square is will give you rho over 3, and they have taken kappa square is equal to 8 pi g is equal to 1. Okay, so there is no any kappa square. Rho is the total density. Rho can be anything with fluid and field. Now here we are talking about only field, so rho is corresponds to the field which I have already seen from equation number 3. Now analyzing with this thing, now here, for example, the Armendariz Picon, they have studied in reference 5-6 concentrated on V phi of the form of 1 over phi squared. Now, in order to derive the cosmological dark energy solution, your potential must be inverse type. Okay, if you don't have the inverse type of potential, then the late time behavior is not possible. And people have also studied the tachyon field corresponds to this f of x. Now if you consider the f of x like this, you will have the tachyon field, and this tachyon field is responsible for the phantom kind of solution, for which you will have omega is less than -1, means that you can get -2, -1.01, and so on. It can cross it. So there are different kinds of functional form exist, and based on these functional forms, so we have different dynamics. Okay, however, we consider one of the simplest form of Lagrangian model for a pure model. P is equal to fx. So we can simply say that we are not considering, we can make it either 1, or you can say that v phi is equal to simply constant v naught. Now since it is a potential, therefore it has the dimension m to the power 4, and f has no dimension. This force, f, the kinetic part, it does not carry any dimension. Now we all know that p has the dimension 4, therefore this is v naught. So they have normalized it that p over v naught is 1, because p has dimension m to the power 4, v has dimension to the power 4, and therefore everything becomes dimensionless. So their p is normalized. So we don't have to worry about that what could be the dimension of fx. So in every paper, people take dimension of the fx as the dimensionless variable. So all other variables can be labeled accordingly. Now, what you can understand with this equation number 6, that if you don't have the potential term in your system, therefore v phi, this v phi is telling you dv over d phi. Now there is no phi, becomes it will 0. If this will 0, this term will go away. We are left with these two terms, and now if you will analyze, this will have the second order derivative and this is first order derivative, and we don't have to do anything much about these guys. And h is also carrying dA over dt into a. Okay, this is complete a. So here is the first derivative, here second derivative, and this is again d phi over dt. So if you will have some kind of a rearrangement, so what you can exactly tell you that instead of x, instead of t, you can make it to dx. Why? Because x is half d phi over dt, then a square. Therefore, if you take dx over dt, it will become d phi over dt times d2 phi over dt squared. Okay, so you can easily express this in terms of phi double dot. Therefore, you can say that, okay, what I can do is that I can change everything in terms of dx over dt in terms of x. Okay, so wherever there is a t appears, I will change it in terms of x. So what they have done here, there is a derivative of d by dt, and here they have changed it and they have introduced like dx and dx over dt. So everything is now finished. Now what you are getting here in x is that the first derivative of x, and here is the only one x. Now this is a very standard equation which people of class 12 can solve it. Okay, now what they have done here, that this dx over dt, again they have again changed it. Why? Here you can see that this is h, and what you can do with h can be rewritten in terms of dA over a and dt. Now if you will solve it, now here what they have only one thing, is that you can take it in the right hand side. Now everything which is depend on x you can borrow here, and that is dA and dA by a. So you have some kind of log of a. So in right hand side you will have some negative and log of a, and with some mathematics you can solve it, and you will have the exactly this one, and k is some kind of an integration constant. This fx square is equal to ka to the power minus 6. So this is a very interesting term here. Now this solution is not new. They have already figured out in different part, and they have given some kind of a label that Chimento have already found out this form. Now what does he do? A nice thing. He thought that now since f is a function of x, and what we can say that now p is containing only f of x. So instead of fx, what we can write here, like p of phi comma x, we can change, because Chiba has examined the Lagrangian of the form. They have first introduced that we can write some kind of an function. Let us say I am writing a of phi, and let us some x, and b of phi some x square. Okay, this is the most general Lagrangian you can have. Now in this case, this a phi and b phi will be considered to be just only your constant. So k becomes k0 and L becomes L0. They don't have too many role here. Now what you can do is that you can say that dp over dx will become a plus 2bx. And we have already seen that when your equation of state can become negative, when your f comma x is going to be 0. If your f comma x become going to 0, therefore your omega becomes minus 1. So what they have said that, yeah, what we can do this, because this p is f, therefore what will happen at the extremum, you can have a is equal to minus 2bx. So we found that x is equal to minus a over 2b. Now this is where your df over dx is going to be 0, and you will get one kind of solution. And from here what you can say that your f is extremum, and if you take the double derivative of f in x square, what you will get is a becomes 0 and you will only get 2b. And based on the sign of b, you will have if b is equal to 0, therefore you can say that f has minima on this. If your double derivative becomes positive, it means that we say that the f becomes minima at this point. So f is minima at minus a over 2b. Now this solution is stable or not, how will you understand? Since there is a minima and we can say that it is an equilibrium point, And if you take any kind of a small variation, like how to find the stability, you have this kind of minima, okay? And if it is minima, then if you vary the function f here a little bit there or a little bit here, it will have to be come around this point. If this happens, we can say that this function is stable in this region. So you can plot f versus x, and you can take that if this is giving you the minima, what you can take is that you can go from like here or here, anything, and then again find it from equation 10. What is the equation 10? This equation. Plug it. Like suppose I am taking the x goes to x0 plus some epsilon, and we will making like dx over dt. This is again a constant number, it's a minima, therefore it will become 0 and epsilon dot. So here it will become epsilon dot, and here we can have 6h f comma x, and x becomes x0 plus epsilon. And if you will take here like epsilon dot and so on, so what will you gonna get? You will gonna get is that epsilon dot is equal to minus 3h. So if your x is x0 plus fx, so you will get f of x0 plus df over dx into x minus epsilon naught. Now, in the analytical solution given by equation 12, this solution corresponds to taking k is equal to 0. Now, what does this tell you about equation number 12? This equation number 12. If your equation number 12, if you are making the k is equal to 0, then what you have? This equation tells you like this. Now, x cannot become 0, therefore f comma x becomes 0, and this f comma x is going to be 0, therefore f becomes constant. So this epsilon dot is telling you that there is no any term of f which is stating that f is simply a constant. Now inserting this equation into equation number 4, and you will get omega is equal to minus 1. Yes, f comma x becomes 0, therefore you will get always minus 1. So the solution behaves like cosmological constant. Yes, the behavior of sound speed, however, is more interesting in equation number 5. It gives sound speed is equal to 0. Thus this solution corresponds to an equation of state equivalent to pure cosmological constant, but with 0 effective sound speed. So if you take the form of f comma x, and if this f comma x has the structure like ax plus b is x squared, the omega gives you minus 1 and cs square becomes 0, which is mimicking the lambda CDM cosmological model. Although the final stable attractor solution in this case to a field with omega is equal to minus 1 and cs is equal to 0, consider how this state is reached. So we are getting that if you have the kinetic type of Lagrangian or kinetic type of Kessence, we will have perfectly all right solution which is mimicking the lambda CDM model, which is actually giving you the dark energy kind of scenario. But more interesting thing is that how this phase has been gone through, because we already know that universe was first radiation dominated, then matter, and this matter as composite with dark matter type of epoch, and then there is comes with dark energy. Okay, now you are getting the dark energy kind of solution, but how this state has been reached? Are you going through dark matter or not? Are your solution is giving you dark matter type or not? So this is what we have to investigate, and this can be investigated by using the same expansion, like you can do the expansion of f of x near the minimum point, and considering the near the minimum point is x0. So what you can realize is that let us reach x minus x0, and then you can take f of x0, which is labeled as f0, and then what you can do is that df over dx and x minus h0, and again you can take one more derivative d2f over dx square x minus x0 square. Why we are taking two more derivative? Because if you take the df over dx, then this will give you one term and this will becomes linear. Okay, and take the second derivative, this will become, so this will vanish and this will have some kind of constant term. So this is all right to expand this function up to second order. Now if you take this kind of form here and put it here into this equation number 12, what you will get is that this one. And if you will investigate a little bit, what you can realize from here, that f2 is giving you the second order derivative, you will get that this x minus x0 over x0 has to be less than 1, where k is constant. Okay, so from here you will realize that whatever we are doing, this x minus x0 over x0 is constant. Therefore in this case, the solution of equation number 16, if you have this kind of case, the solution of this equation number 16, in which your x becomes x is equal to x0 plus epsilon a over a1 to the power minus 3. Now this solution in which you are getting this point, epsilon into a over a1 must be lesser than 1, because what you are doing is the Taylor series expansion, and you are demanding that in order to fulfill this kind of situation, which is satisfied by this equation number 15, where it is giving you that epsilon 1 a over a1 to the power minus 3 has to be less than 1. This gives the physical meaning of epsilon 1 and a1. Our solution will be valid, that is equation number 17 will be satisfied for a is greater than 1. Now this can happen because you can see here that this is a1 cube over a into epsilon. Now a has to be greater than a1. Okay, and this a1 is again one of the constant. Then again epsilon has to be less than 1, and from there we will get the equation number 19. Okay, now if you will take the rho is equal to 2x f comma x minus f and put it this f solution list, equation number 15 and equation number 18 here, then what we are understanding that rho will have some kind of form like this. Now if you are putting all these x and f comma x, then what we will realize that rho has some kind of f naught which is constant, and having this term epsilon to a by a1, which is already fixed there, that a has to be less than a1. Okay, sorry, a must be greater than a1 and epsilon has to be less than very much 1, and then again some higher term of a over a. Now this rho having this minus 1, what does it imply? In lambda CDM model, which is responsible for dark energy, in which the energy density come out to be constant. Okay, and it is demanding that this f0 must be less than less than negative, because if you don't have f0 negative, then rho becomes negative, and this cannot be possible. Your energy density has to be positive. Therefore what we are saying, that we are getting some kind of a positive rho solution, and this positive rho solution is telling you about the some kind of energy density which you are getting from a lambda CDM model. Now here interesting part is coming, that rho and there is a scale factor a, and rho and scale factor f2 is again at the minimum, so rho is proportional to a to the power minus 3. And when you have this much case, we have studied in the standard cosmology that if you have a dust kind of solution, then your rho is depend on a to the power minus 3 as a dust, and in radiation case your rho will be a to the power minus 4. Therefore what we are getting here is that one rho, the higher order term, is a constant which is mimicking the lambda CDM model, and the second term is exhibiting the dark matter, means a dust type of solution. So this is a very interesting case, and we can neglect safely that okay, it is a very term, because now you can see that a to the power minus 6. So what we are understanding, that the rho becomes, so if this kind of case, then dynamically rho becomes constant. And if you just see, because if you are plotting here where rho becomes constant, and so what is happening, that some before the rho is varying like a to the power minus 3 here, and then it is becoming like constant. Okay, so as you go late time here, suppose this is a log a or a, you go late time, you will have the rho constant, and if you go in the early phase, you will get it near to the solution of this thing, your Kessence can behave like a dark matter phase. So that is a very interesting thing. They have already said f0 has to be less than 1, less than 0. And if you will put the equation 15 into cs square, like cs square is p, you already know that what is the f here, and then we have the rho here, and cs squared is df over dx over d rho over dx. Then what we are getting is x minus x0 by 3x minus x0, and from here you will get only this kind of term, epsilon 1 a over. We have already assumed that epsilon into a has to be very much, a cube has to be very much smaller than 1. What does it implying? That in the dust epoch, the sound speed of the field was very small, which is telling you that the universe has gone from dark matter phase and then entered to dark energy phase, and in dark energy phase rho becomes constant, which is implying that you don't need any Chaplygin kind of gas. The kinetic quiescent can itself unify dark matter and dark energy, and it also handles the cosmic coincidence problem. But this kind of model has a different kind of instability to explain different things. Okay, so we will talk about in different, and in my research I have already shown what are these kind of instability you can see if you have only quiescence, kinetic quiescence in your theory. So I hope you find this very useful, and if you find this, please like and subscribe my video. Thank you very much.